So this paper presents an efficient energy-based adaptive duty cycle scheme for energy harvested wireless sensor network, presented by Dr. Nivine Guler and Dr. Zaid Ben Hazem from the Department of Informatics Engineering and Department of Mechatronics Engineering, University of Technology, Bahrain. First, we shall present the content of this presentation, which is an introduction to the main concept, along with the motivation, the system structure with the proposed algorithm, the simulation results, conclusion, and future. The main motivation behind this paper is that in literature, most medium access control, the MAC protocols for the energy harvested wireless sensor network did not consider the effect of the dynamic nature of energy harvesting. On the other hand, they consider it as a static, which is not true. The predicted energy harvesting factor and the integration of the duty cycle of the sensor nodes with the predicted harvested energy weren't given so much consideration for the purpose of enhancing the system performance. Hence, in this paper, we have presented the EADS EHWSN, which is a MAC protocol that is prediction-based energy harvesting with an adaptive duty cycle depending on the predicted energy harvesting amount and the geographical distance of the nodes. Presented or the proposed network architecture, as we can see that here, based on a cluster, it's a cluster-based network where we have a cluster head and members of nodes belonging to each cluster, and we have a hub that is acts as an external energy resource. The flow chart of the algorithm starts with the cluster head. It calculates the predicted energy, then it calculates the duty cycle. It broadcasts peak, including its duty cycle to all its members, and all the nodes send their data to the cluster head, and accordingly the cluster head will prioritize the packets, meaning it will start with the high priority packet. Starts processing with it, and before processing it will check its remaining energy if it is above the required energy for processing. If not, it will switch to harvesting mode, and it will broadcast to all the sensor members to go for sleeping. And once the battery is full, it will continue with where it stopped. It will check if any remaining packets are there for the high priority, continue processing with it. If the remaining energy is higher than the required energy for processing, it directly processes it, and it will calculate again the remaining energy that it has, and accordingly it will find the mean absolute error, and it update its duty cycle. It will broadcast its duty cycle again to all its members, and accordingly it will continue with the non-priority or low priority packets, and so on. Proposed frame structure starts for the cluster heads and for the sensor nodes. For the cluster head, at time, which is called TDC for the duty cycle, and then there is a waiting time to receive the data from the sensor nodes, and there is a TR, which is the receive and sort the data according to the priority of these packets, and then it will check its duty cycle again, and the TPC, which is the processing with high priority, and calculate the performance metrics. For the sensor node, there is the listening mode, which their sensors will stay as the listening for their cluster head to receive any acknowledgement from their cluster head upon receiving the data. Through the deep learning neural network for the energy prediction, first we have to make sure that the power and the energy needed for the harvesting energy are stated clearly. For example, equation 1 states the formula for the energy, for the harvested energy, equation 2 and 3, they represent the transmission power for transmitting the data during time P for the processing, and as in equation 2 and 3, and is given by equation 4, and the maximum rate of sensed data for the intercommunication, which is the communication inside the cluster, is limited by the minimum rate of transmission and is given by equation 5. So the total system achievable rate is given by equation 6, and equation 7 and equation 8 represent the wasted energy of the cluster head and that of the sensor node. Total energy consumption of the cluster head is given by equation 9, and that of the sensor node is given by equation 10. Therefore, the total energy consumption in the system is given by equation 11, and hence the cluster head calculates the duty cycle, which is given by equation 12. Therefore, the DNN model, it uses the previous HAP energy harvested value for forecasting the harvested energy for the next time cycle. So the proposed protocol combines the predicted energy harvested information from the DNN model with the geographical location of the sensor node to enhance the network performance by updating the duty cycle adaptively in each cycle. And this below figure, it shows the details. Here we have 10 hidden layers. We have one input layer and one output layer. For the end-to-end delay is given by equation 13, which is the time it takes the packet to be received at the destination and going back to the sender. So here it includes the processing delay, the queuing delay, the propagation delay, transmission delay also. And the equation 14, it represents the packet delivery ratio, which is the ratio of the number of received packets to the number of transmitted packets. And the equation 15 represents the average network throughput, which is here the NF is the amount of the data packets received by the receiver over the total simulation time. Of the performance of the proposed scheme, we have used the Green Castelia for implementation and compared the network performance with the state-of-the-art protocols as in reference 15, 16, and 17. And here we have the data set that consists of 13,800 samples adapted from the reference 18. And the network consists of a single hub providing power and one sink located at the hub, and we consider a cluster-based network. Sensor nodes send their monitor data to the cluster heads, where the cluster head aggregate the data and send them back to the sink. We assume nodes are randomly deployed in 30 by 30 meter square field. Simulation have been carried out for 50 times with the confidence interval of 95%. The time cycle is chosen to be 10,000 seconds. As a conclusion, we can see that the energy harvesting becomes a promising solution, especially for constrained battery devices such as the wire sensor network. So the proposed protocol is based on the duty cycle, and each cycle is adapted to the new predicted energy harvesting value. Hence, the duty cycle is formulated in terms of predicted energy harvested, node location, and the number of the packets sent, and the battery capacity of the sensor node. The end-to-end delay, the energy consumption, the network throughput, and the packet delivery ratio network metrics have been studied for the proposed scheme. which showed an increased enhancement with the state-of-the-art, like the HADC by 21%, the ESMAC by 74%, and the PADC MAC by 39%, respectively. And for the future work, the proposed EADC EHWSN can be modified to include the feedback from the DNN model that affect the predicted energy harvested value, and this could be applied to health applications and wireless body area networks. Thank you so much.